next week if we finish trig substitution early and just going on to the next section, and I'll warn my online students it might happen, but we shouldn't have another week where we're sort of treading water. So one rule left, Simpson's rule. It looks kind of similar to the trapezoidal rule, but its derivation, we're actually not going to show the derivation because the derivation turns out to be complicated, but we can certainly get at the idea behind Simpson's rule. And the idea behind Simpson's rule is very similar to the idea behind the trapezoidal rule, that instead of using rectangles, we should use some other shape that's doing a better job of tracing the curve. So let's say we have a function on A to B. I mean, just as a side note, I keep talking about like these rules in terms of area under the curve. It's an easy picture to draw. This all works if the function is negative. I mean, you're no longer getting the area under the curve exactly, but there's nothing about any of this that requires the function to be positive. So instead of writing down just the one interval, I'll write down two intervals. And that will give me 3 points. And except in kind of aberrant situations, like when the points all lie on the same vertical or horizontal line, through any 3 points, we can fit a parabola. And a parabola is a quadratic polynomial. So if this is x0 and this is x2, finding the area under a parabola is something that we can do. And because parabolas are curved, they do a much better job than anything else we've looked at before of approximating curves. But we're going to have to sort of shove a lot of the details under the rug here. Like, yes, through any 3 points, there is a parabola, but first finding the parabola and then finding the area under the parabola, we do wind up with a very straightforward formula in spite of those issues. So it's a bit, it starts very complicated, but then really simplifies at the end. And as well, let's see, not that PI calculator still. We're going to have time. I might as well do an example with this. So just pausing fast slightly while I get my calculator up and running. Anyway, Simpson's rule a little like the trapezoidal rule, as I said. The integral from a to b of f of x dx equals. So with the trapezoidal rule, I said that it would be nice if the intervals were all of the same size. But I mean, you can use the trapezoidal rule for any function in any instance. You can always draw the trapezoids. Simpson's rule is different. Simpson's rule needs these intervals to all be the same size. And that's just because, I mean, if you think back to the trapezoidal rule, I mean, the worst case scenario is that you're finding areas of trapezoids, and you can do that. It's the average of the heights times the base. For Simpson's rule, you're doing something really complicated. You're fitting a polynomial, and then you're finding the area under this quadratic. So, I mean, this is not something that would ever make sense to do by hand. So we need this simplification for our formula to come through and to be nice to use. And the trapezoidal rule has a delta x over 2. Simpson's rule has a delta x over 3. And now inside the parentheses, we'll also have something that looks familiar from the trapezoidal rule, which is that we're going to have a bunch of terms added together, and the first term and the last term won't be multiplied by anything, but all of the other terms will be multiplied by something. With the trapezoidal rule, all of the other terms were always multiplied by 2. Simpson's rule has this pattern where the terms are alternately multiplied by 2 and 4. This is not a real problem, and I'll come back to why not in a moment. But Simpson's rule has another strict requirement that the other rules, the midpoint rule and the trapezoidal rule, do not have. And that's with the midpoint rule and the trapezoidal rule, we could have as many intervals as we want. With Simpson's rule, we need an even number of intervals. And that should be pretty apparent just looking at how this rule works. 2 intervals to get the 3 points we need to fit the polynomial. If we want to keep going, this point, and this point, we can fit the polynomial between them. The first polynomial is giving us the area of the first 2 intervals. The next polynomial is giving us the area of the 2 intervals after that. and so on. So intervals have to be added in pairs because we need 3 points. So Simpson's rule is a good rule. Maybe that sounds sort of fatuous, but the midpoint, the trapezoidal rule and Simpson's rule both have a lot of very powerful real world use cases, whereas the midpoint rule is left kind of out in the cold. And if I azoidal trap, azoidal trap, azoidal trapezoidal rule and Simpson's rule. So trapezoidal rule, there's a very clear use case. Trapezoidal rule can be used when the data is stored in tables. Ideally, the data will be equally spaced, so we can use that quick formula instead of actually finding the areas of a bunch of trapezoids. But no matter what the table is, the trapezoidal rule can be used with it. That's not true of the midpoint rule. It's not true of Simpson's rule. That's where this requirement bites us. If we can't control what the data on the table is, then we can't use Simpson's rule because Simpson's rule has these requirements. And Simpson's rule, unlike the trapezoidal rule, will just totally break down if you miss an observation. So, and the midpoint rule doesn't work just because if you have data on the table, you don't have the midpoints. You have the data that you have. So the trapezoidal rule is very good in that real world use case. Simpson's rule is very fast. It's good when you have an equation. So, you know, this is the stuff we're used to. You've got an equation for the function, but you can't use the fundamental theorem because you can't figure out what the antiderivative is. So between data, and I mean, I guess I'll say that the trapezoidal rule also works fine if you have data, you know, stored in graphs. I mean, just if you actually have a graph, you can just read these values off the graph. And use the trapezoidal rule this way. The trapezoidal rule is faster than the midpoint rule, but slower than Simpson's rule. What do I mean when I talk about these rules being fast or slow? I'm talking about numerical speed. Like if we want to use a computer to estimate an integral, how long is it going to take us? And the difference here, I mean, computationally, neither the trapezoidal rule or Simpson's rule are complex. You multiply, you divide a number by 3, you do some multiplication, you add your products together. This is something where a computer can easily do this with hundreds of thousands of data points in a split second. But when we look at n, how many intervals do we need before the approximation becomes good, which I'll put in quotation marks. When we're doing numerical approximation, we have some kind of margin of error that we're willing to tolerate. We want our answer to be correct to 5 decimal places or whatever. And we know that the more we cut this interval up, the better our approximations become. So to get an accurate answer, we need some number of intervals. You know what I have on the board? I'm not going to count, it might be 16. That's probably, if you're using the trapezoidal rule, going to give you a pretty accurate result. If you're using Simpson's rule, it's going to give you a better result. If you have n fixed, Simpson's rule will be better than the trapezoidal rule. And that gets reframed in terms of speed, because you need fewer rectangles to get a good result. You need to do fewer additions and fewer multiplications and fewer computations, and Simpson's rule is faster. And like I said about the midpoint rule sort of being left out in the code here, well, we can't use it for tables. I guess we could use it for graphs, but we can use the trapezoidal rule for graphs, and that's faster. If we have a function, it's always going to be Simpson's rule, because Simpson's rule is the fastest rule we have. And if we have a function, we are deciding what n is. So we don't have to worry, does it have an even number of intervals or not? We can just decide, well, this is the interval we're working on, I'm going to use 10 intervals. So this is not a real issue in that context. And I mean, the obvious sort of question, why do we teach the midpoint rule? I mean, it probably comes down first to just tradition. I mean, I'm gonna be brutally frank here. The calculus curriculum has not been revised in a long time, and it probably ought to be. But I mean, also because because it does serve as a logical starting point. You know, you ask the question, how can we numerically approximate integrals? And maybe the first thing you say is, well, we have a tool sort of explicitly created for that purpose. The Riemann sums are how we've sort of found the area under the curve. So we can use Riemann sums to approximate integrals. And then we ask, well, how can we make it better? How can we make this approximation be as good as possible? And we say, well, when you have a Riemann sum, the points you use could be anywhere in the interval. We notice that the Riemann sum gets better if instead of just choosing points at random, we use the midpoints. And then we ask, well, how can we make this even better? And then we abandon rectangles and we go to trapezoids. And we ask, well, how can we make this even better? Just in terms of speed here. And we wind up at quadratic curves. And I think the feeling is that if we just skip the midpoint rule, we're kind of missing a step here. So the midpoint rule might not see a lot of real world application, but it's still a step in this ladder that winds up here. All right, so I said, and I'll get this in the recording as well. This week was sort of ended up being kind of goofy. I didn't want to start this complicated topic right before the test, but the end result is that this, this one section that didn't really require 3 days, probably 2 days, got stretched out to 3 days. And I'll post an announcement that I don't want this to happen again. I mean, it's my fault, but next week we'll do trigonometric substitution. And if we finish that early, we are moving into the next section. So the plan is to cover one section, but if we cover 1.5 or 2, that's just what happens. And I'll get, of course, I know that I owe you your tests back. I'll get those graded and the grades posted probably today. And I will see you Monday.